Bonjour, I am Abraham DeMoivre, a French mathematician from around 16-something. I was a respected intellectual, a part of the Royal Society, and made my money off playing chess. I explore concepts of probability, distribution, and linked complex numbers and trigonometry.
I'm Isaac Newton. We were close friends. So close, in fact, that when people asked me about my concepts, I would tell them, "Go ask Mr. DeMoivre. He knows these things better than I do." In 1707, he derived his famous formula, and in 1722, simplified it to the form we know and love.
Earlier this term, we saw that when multiplying complex numbers, the end result would have the sum of their angles and the product of their magnitudes. In this example, we're going to look at the complex numbers 3 plus 4i and negative 5 plus 12i. 3 plus 4i, which is in quadrant 1 if you were to graph it on a complex plane, has a magnitude of 5 and an angle of 53.13 degrees. This can be found using a Pythagorean theorem as well as tan, cos, sine. And negative 5 plus 12i is in the second quadrant and has a magnitude of 13 and an angle, namely alpha, of 112.62 degrees. When you add them together, we see that is 165.75 degrees. Now, if we multiply them together, we get negative 63 plus 16i. This is also in the second quadrant. And when you find the magnitude, you get that it is 65, which is, not surprisingly, 5 times 13, which are the magnitudes of the first two complex numbers. And then this is easier to see when graphed, but the angle that we get using the complex number negative 63 plus 16i is 165.75 degrees, which we saw was the sum of theta plus alpha. The same concept applies when multiplying a complex number by the same complex number. Let's take a look at 3 plus 4i. If we were to square it, the theta measurement would be 2 times theta, as you would be adding the same angle twice. And the magnitude, which is 5, would multiply by itself, so 5 squared equals 25. Thus, the end result to 3 plus 4i squared would have an angle measurement of 106.26 degrees and a magnitude of 25.
The most practical application that our class has discovered for DeMoivre's theorem is for complex numbers in polar form. When raising r cis theta to the nth power, DeMoivre's theorem describes that the result equals r to the n times cis n theta. This simplicity results in a much more efficient squaring and exponenting of complex numbers. Furthermore, it can help us find complex. If you know a complex number in polar or rectangular form, you can put it in appropriate polar form and solve. For example, given the equation z to the fifth plus 1 equals 0, we know z to the fifth equals negative 1, so it could equal cis 180. Z is to the fifth, so we know there are 5 different roots that form a pentagon. We know that cis 180 is 1, and we move 1/5 of 360, 72, the interior angle of a pentagon, around to find our other roots, cis 108, cis 36, cis 252, and cis 324. The magnitudes are all 1 in this case. Simply put, to find the root of a given complex number, ensure it is in polar form, set it equal to r to the n cis n theta, and solve for the roots, depending on the number of roots asked for, or the given n, depending on what they give you. Then, knowing the roots will form a regular, repeating as you add 360, shape, solve for the other roots once you have 1.